So we're on time. So welcome back. And so now we have to finish this morning. We have the beginning of a second mini course by Allan Sly, who's going to talk about phase transitions for the random constraint satisfaction problems. Okay.
Thank you, and thanks so much for the invitation to this wonderful workshop. It's been great to hear about just the really exciting advances. So Nathaniel asked me to talk about sort of random KSAT and things associated with that. It's a bit further away from most of the topics of the workshop, so I'll try and give a sort of gentle introduction to the area. So today I want to just introduce what I mean by a random CSP. I'll look a bit at the example of colorings on a random graph. Talk about belief propagation and sort of how this yields sort of predictions for different phase transitions. In the second part, tomorrow I'll talk about particularly what happens in sort of more homogeneous graphs, random regular graphs, and calculations you can do there. And in the final part I'll talk about the random KSAT model, which is a much more heterogeneous sort of random constraint satisfaction problem. Okay, so just to begin, what is a constraint satisfaction problem? Well, it's basically just what it sounds like. You have a collection of variables and a set of constraints you want them to satisfy, and you ask, can you satisfy all the constraints simultaneously? So imagine solving a system of equations, coloring a graph, satisfying some Boolean formula. And because we do probability, the constraints we choose will be chosen randomly, either sort of uniformly at random IID from some distribution or according to some other random rule. Okay, and so I just want to start off with a collection of examples, and maybe the most canonical one would be sort of combinatorial properties of random graphs. So you imagine you take some model of a random graph, Erdős-Renyi random graphs, or a more sort of regular one, the random irregular graph, where all of the vertices have degree d, and it's chosen uniformly according to that. And we could ask, does the graph have a proper Q coloring? So can you color all the vertices with Q colors such that all of the neighboring vertices have different colors? And this is a constraint satisfaction problem because the variables are the colors of the vertices, and the constraints are the edges. They're saying that the neighboring vertices have to have different colors. And because the edges are chosen randomly, because it's a random graph, it's a random constraint satisfaction problem. Okay. Another example would be, can you find a large independent set on one of these graphs, and what sizes can you find? And so an independent set would just be a subset of the vertices which no two of which share an edge. So in a coloring, say the red vertices form an independent set. Okay. So another question, which and so I should say, these are just motivations, and for most of these we don't know the answer to them yet, but there are predictions. Okay. Another question that I just heard recently was a question of when you have a regular subgraph of an Erdős-Renyi random graph. So you can talk about the k-core of a graph, which is the largest subgraph of your graph, which such that all of the vertices have degree at least k. And there's a really simple algorithm for constructing it. You just delete all the vertices of degree less than k. Maybe this makes some of the vertices that are left are now of degree less than k, so you delete them and you keep going until you only have vertices left of degree at k or larger. And so you may end up with just nothing. Otherwise, what you're left with is called the k-core of the graph. And this because of this sort of fairly simple algorithm for constructing it. It's pretty well understood. There's a sharp threshold in the density for when you have a k-core. But of course, some of the degrees will be bigger than k, so you can ask, is there a k-regular subgraph of the graph? And this also has a sharp threshold. And so you can ask, are they the same? If you have a graph where all of the degrees are bigger than k, will you have a regular subgraph of the k-core? And in the case of k equals 3, Bolabash, Kim, and Verstraete showed that no, you don't. It's sort of just by calculating the expected number of them. And so you can ask, what about bigger values of k? So there are some conjectures. They made the conjecture that when k is greater than or equal to 4, these thresholds will be different. An alternative conjecture is yes. Okay. So one of these is going to be wrong. At least one, I guess. It could be. And so the first group are essentially in combinatorics. The second group are physicists. They and their analysis was using essentially the tools that I'll talk about this series of lectures, and so depending on how you feel about that, you may have more or less confidence in which prediction to believe. Okay. Another sort of question you could ask is, people in random graphs are interested in, is when you have a Hamiltonian cycle, so just a path that goes through all of the vertices exactly once. And so it's been known for a long time, that if you have a random deregular graph for d at least 3, you always have a Hamiltonian cycle. But it's a sort of notoriously unsolved question of, if you have half of the vertices of degree 3, half of the vertices of degree 4, do you have a Hamiltonian cycle in such a graph? And somehow the calculations that you do in the regular case just don't work. But you can sort of encode this as a random constraint satisfaction problem too. In an Erdős-Renyi random graph that's sparse, you won't have a Hamiltonian cycle because there'll be isolated vertices for a start. But you could at least ask, what's the sort of asymptotic length of the longest path? And finally, the last CSP that I'll be talking about in the third lecture is one that originates in computer science. It's a model of a random Boolean formula. And the idea is you have n Boolean variables that are either true or false. And then the constraints or clauses, you take k of the variables or their negations and take the or of those. You want at least one of those k variables to be evaluated true. So and then the formula is you take the and of these clauses. So a clause is like, so for 3 sat would look something like this. The or of 3 variables, you can also have the negations. And in the random k-sat model, you just choose the variables uniformly at random. Okay. So obviously, the more constraints you have, the harder it will be to satisfy all of them simultaneously. So we can sort of parameterize the problem by the constraint density, and the right scaling to take is the ratio of the number of constraints divided by the number of variables, and I'll call this alpha. And we sort of wonder, for which values of alpha do you see solutions? I'll also mention a variant of the model called not all equal sat, which is just the k-sat problem, but you ask that both x and its negation, you negate all of the xi, satisfies satisfies the formula. And somehow this should have the same set of phase transitions, but it has some extra symmetries that make it more tractable. So some results, this not all equal sat model is the only one we know them for. And it's called not all equal sat because if you look at a particular clause, it means that at least one of the variables has to evaluate to true, and at least one has to evaluate to false. So they're not all equal. Okay. So the kind of questions that we'd like to be able to answer, the first is just when you have solutions at all, so the satisfiability threshold, how many constraints can you put on such that they can all be satisfied simultaneously? And once you know that, we could ask further questions. How many solutions will there be? What does a random solution look like? And perhaps the hardest question is sort of algorithmic ones. Can you find a solution in a sort of efficient way? That, I think, much less is known about. Okay. So I want to begin by talking about, oh, no, actually, I just want, okay. It mentioned that, actually, before I do that, we can think of, it's a useful lens to look at these problems is to think about the distribution over solutions. And that will be a spin system, like one of these statistical physics models, like the Ising model. So just each of the variables we can think of as taking some value, and then there's some interaction which will just be so in the case of coloring, it would just be saying that the neighboring variables have to be different. So we could write the distribution over solutions as 1 over a partition function, which will just be the total number of solutions, times some weights that essentially just encode the fact that this is a solution. So in the case of colorings, this would just be Z, the partition function would just be the number of colorings, and the product would just be saying that on each edge the neighbors are not equal. But at times we'll want to look at weighted solutions for reasons that will become clear later on. Okay, so I want to start off by discussing the case, sort of a very natural example, random colorings on Erdős-Renyi random graphs, and trying to understand when you have colorings. This is a problem there's not yet solved, although there are quite good bounds for it, which I'll describe. But so natural approaches to understand when you have solutions is to just try and count how many solutions you have, and the sort of limit of log of the number of 1 over n times log of the number of solutions, the sort of normalized log partition function, or called the free energy. And so the simplest sorts of things we could do is just try and calculate its moments. The first moment will give sort of an upper bound, and the second moment method can potentially give a lower bound. And if we were luckier, which we're not, these would match each other. Okay, so I'm going to do this calculation in 3 different ways, and I'll start off with the wrong way of doing it. So we could just take the expected value of this partition function for the Erdős-Renyi random graph, and okay, and these are easy to calculate. You just, like for any coloring of the vertices, just assignments of the Q colors to each of the vertices, you can work out the probability that it's colorable, and so Ci will just indicate how many vertices are colored I, and then there'll be a multinomial for how many ways to do that, times the probability that that particular configuration is colorable. And it just means that all of the edges that join 2 vertices of the same color have to be different. And so, we could actually, when you look at this sum, there's sort of we're summing over the CI, which is sort of the empirical distribution of how many colors you have. So how many colors you have for each vertex. But in this, so in a sense, you'd want to optimize over what sort of empirical distribution gives you the biggest value. In this case, that's an easy problem to do because, well, there's two terms. This first one is essentially an entropy term, how many ways you can assign the colors, and the way that has the most is just have balanced numbers of all of the colorings. That's the maximal entropy distribution. And it's also the way of coloring the vertices that has the highest chance of being a proper coloring because you have the fewest number of edges between the vertices. So if you just believe that the main contribution for this will be when the CI are all equal to 1 over Q, we get this formula. Okay, and so our prediction for the growth rate of the number of colors would be like log Q minus d over 2Q. So another way we could do it is say, okay, you have your Erdős-Renyi random graph, with edge probability d over n. So most of the time, the number of edges in the graph will be approximately dn over 2. So let's condition on the number of edges. Do the same, the sort of formula conditional on that. So then we just need to check what for each of the m edges we throw down, the probability that it doesn't connect two vertices of the same color, and continue, do the same calculation, and we get a different formula. Okay, something that's slightly less. So, and I'm going to claim that this is the right calculation to get the sort of typical number of colorings of a random of the Erdős-Renyi random graph, and it's because essentially we're doing something like what Wendelin was talking about, where we have a random graph model, and in the expected value you're essentially weighting it according to the number of colorings here. But we're interested in not that weighted model, but the the graph without the weighting. So, and so this is a very simple example of because okay, if you look at the Erdős-Renyi random graph, most graphs will have dn over 2 edges. It's a large deviation event to have sort of a substantially different number of edges. But on the other hand, graphs with fewer edges will have a lot more colorings. So you have, so if you're not conditioning on the number of edges, the dominant contribution will come from graphs that just have substantially fewer edges than the typical graph. So to get the sort of right behavior for the typical number of colorings, you should condition on the number of edges. So this is okay. This isn't anything deep, but in some sense, in more complicated settings, being able to calculate partition functions in a way that don't tilt the graph towards very rare graphs is one of the key issues that you have to deal with in this theory. Okay, let's calculate the typical number of solutions. And sorry, I should say also this gives you an upper bound on when it's colorable as well, of course, by looking at the point at which this exponent becomes 0. Okay, so let me give a third way of how you might go about calculating the typical number of solutions. And this is really a heuristic for what happens when you add in an extra vertex. So we go from a graph with n vertices to one with n plus 1 vertices. Okay, and we want to compare the log of the number of colorings in the two graphs. So what happens when you add in an extra vertex? Well, one is you have a new vertex and it has about Poisson d number of neighbors. That's the typical degree distribution in these random graphs. But also with the edge probabilities in the whole graph decrease. So you go from d over n to d over n plus 1. And the sort of aggregate effect of that over all the vertices in the graph is that you should also remove a Poisson d over 2 number of edges. Because otherwise and this will mean that on average, where every time you add a new vertex, you add d over 2 edges, which gives the right sort of edge density. So you need to take into account both effects. And so we could think of it as, like if you look at the expected difference of the logs, there'll be some vertex term, some edge term. And now, if you make an assumption that is that when you're adding a new vertex to the graph, you're connecting it to independently chosen vertices in the graph. Hopefully, the sort of marginal the distributions on those ones looks like a product measure. This assumption won't always hold, but if it does, then and that it was a product measure and they were sort of a product uniform distribution, then you could work out that the effect of adding in a new vertex would be like this. This is log Q for the possible choices of the color, and then this term for the probability that all of the edges were, not monochromatic. And then there's a similar term for removing the effect of removing Poisson d over 2 edges, and all up you get this formula, which was the same one we did in the calculation on the previous slide, the expected value condition on the number of edges. Okay, so that and it turns out some of the time just doing the expectation won't give you the right answer, but this prediction of working out what happens when you add in a new vertex, go from a graph of size n to size n plus 1 is sort of a more robust way of doing the calculation. So, okay. Okay, so that's the first moment. We could also work out the second moment, and calculating the second moment is really like calculating how many pairs of colorings you have. And a pair of colorings you can also think of as a constraint satisfaction problem. You just, where every variable is a pair of colors, and then the edges say that in both variables it has to be a color. You have to have different values. So, okay, so we could write down the expected value of this. Now Cig will be the number of vertices that are colored I in the first copy and colored J in the second copy. And this is the probability that none of the edges violate the coloring rule. Okay, and so again you get a term that looks like that's the entropy of the Cij, and a second term for that corresponds to the probability. But now it's more complicated because the entropy will be sort of optimized when you have just the two colorings are balanced and independent of each other. All theCij's will be 1 over q squared. So if you look at a vertex, it's blue with probability blue in one copy and red in the other copy with probability 1 over q squared. But the second term turns out is not optimized at that. So there'll be some trade-off. So you can ask what choice maximizes the exponent here. And okay, so it turns out that this is not convex and can have multiple maxima. And in general, like if Q is big, it's optimization over quite a lot of variables. So, okay, but you have to analyze that. But let's just to make our lives simpler, imagine we just look at a simpler distribution of Cij, or family of Cij, just ones where, so we can think of this as a q by q matrix, and we could just look at ones where it's constant on the diagonal and constant off the diagonal. So t in this parameterization t equals 1 would mean that all of the Cij are just 1 over q squared, but t equals q would correspond to 1 over q off the diagonal and on the diagonal and 0 off the diagonal, and that just means taking two completely identical colorings. So in the and then if you, in which case you'll just get the first moment. You're counting pairs of identical colorings is just like counting colorings. Okay, so suppose we look at the case of q equals 30, and in this parameterized family of empirical distributions, the maximum, so this is with average degree 198, the maximum does occur at 1, just for completely independent colorings. But there's another maxima that's sort of close to it. But still, the main contribution will come from here. And roughly speaking, having sort of pairs of independent solutions giving the biggest contribution will correspond to the second moment method working. So the second moment being the same as the first moment squared. And that's what you want in order to be able to get something out of the second moment method. On the other hand, if we increase the average degree to 199, now the other maxima is the biggest one. You get a bigger contribution from pairs of colorings that are very close together, that only differ on a small set of values. And so in this case, the second moment will be much bigger than the first moment squared. And so you can't hope to apply the second moment method, at least to this random variable. But the typical value will be far from the expected value. Okay, and essentially the problem is that you have lots of pairs of colorings that are close by to each other, that only differ in a small on a small number of vertices, and this is essentially the phenomena that colorings are coming in clusters. If you have one coloring, you'll have quite a lot of nearby ones, and somehow one of the big issues in this theory is dealing with effectively with the clustering of the space of colorings, and in general the space of solutions to the random CSPs. Okay, and so maybe let me just summarize what's known about the chromatic number, and it's so Akliopoulos and Naor sort of did this sort of the full second moment calculation, and so it works pretty well, at least in the sense that if you look at random Q colorings for any D, you can nail down how many colors you need to color the graph to one of two possibilities. It's either QD or QD plus 1 is the chromatic number, the smallest number of colors to color the graph. And this is just a careful version of the second moment method. The ratio of the second moment and the first moment squared will converge to a constant, but the constant won't actually be 1. So that just tells you that the number of colorings is positive, and that you have a coloring with a probability bounded away from 0. But there are results about sort of sharp thresholds by Freegut, which say that if you look at a slightly smaller value of D, then the probability of being colorable will tend to 1. So the first moment gives you some sort of upper bound where it's not colorable. The second moment gives you some lower bound where it is, but there's still some gap in the middle. And but there are predictions for where the exactly where the threshold should be for Q colorability, and well, so I hope So hopefully I'll explain how you get to that threshold, but that's still an open problem.
What is it? On the right, it means probability of it being colorable.
Oh, so this means like the above this threshold, the probability is tending to 0. Yeah.
And on the green, it goes to 1.
Yes. Yeah. So.
And in the middle, the probability is somehow,
Okay. So that's a.
It's the limit when n goes to infinity.
Yeah. So we could look at probability of being Q colorable, and this will be some function of n, and 1, 2. So as n tends to infinity, below d2, where the second moment method works, it will be sort of converging to 1, and above d1 it will be converging to 0. And Freeguet's result, which is really a general sort of theory about sort of Boolean functions, although I guess in this case they're not exactly Boolean, but sharp thresholds for Boolean functions, says that the way, as n tends to infinity, the way it comes down from 1 to 0 will be a sharp threshold, in the sense that going down from 1 minus epsilon to epsilon, the window there will tend to 0 as d is going to, or as n is going to infinity. But Freeguet's result is, in a sense, a bit too abstract, in that it doesn't tell you where that happens, and it also doesn't tell you that the location of where that happens converges. It could, in principle, it could be crazy, and for even values it's here, and for odd values it's here. And so it doesn't say that there's some sort of limiting critical value of d, but for any fixed n, this graph looks more and more like a step function. Okay. Okay. So it's important to sort of think about the way these colorings or solutions to the random CSPs look locally on the graph. So locally the graphs look like trees. In the Erdős-Renyi case, it will look like a Galton-Watson branching process. In the random regular case, just a regular tree. And so we could look at colorings on trees, and on trees, it's very easy to calculate the marginal probabilities of vertices for colorings and other spin systems, because you can do it essentially recursively using dynamic programming. So we want to define the message from a vertex u to a vertex v, which will be a probability distribution over the colors, as the probability that the vertex is in state x, given just this tree rooted at u, where you delete the edge from u to v. Now, in the case of colorings by symmetry, it would always just be 1 over q, but we could imagine that there's some fixed boundary condition here. So in this case, the message from u to v would be that it's this vertex. Essentially, the boundary condition just means that it can't be green. So the message would just be it's red with probability half and blue with probability half. Okay, and we could define this for all of the edges of the graph. So this one, because it's got a red and blue boundary condition would just say it has to be, is green with probability 1. And the useful thing is that you can sort of define these recursively. So if I want a message from U to on the directed edge from U to V, so the message that U passes to V you can define that in terms of all of the other incoming messages from the other neighbors of U going towards U. So if you know the d minus 1 incoming messages, you can work out the other outgoing message. In the case of colorings, this is the formula, and the reason why you can do this is that these messages are really saying that, okay, if we didn't have these edges here, what would the marginal at U1 be? What would the marginal at U2 be? What would the marginal at U3 be? Then we want to look at the graph rooted at U. So we just want to know what is the effect of adding in these edges. In the case of coloring, the probability that this is, say, blue is just proportional to the probability that none of the children are blue. So you can set it as so this would be the formula you get. So on this edge from V down to its rightmost child, you'd get 1/5, 2/5, 2/5. Okay, and so in linear time, you can work out all of the messages on the graph just recursively, and from these you can calculate lots of things. So I should say it doesn't just work for coloring. There's an analogous formula for any of these spin systems. Okay. And I want to stress that this will be important because our understanding of the cluster of solutions will be defined exactly in terms of these sets of belief propagation messages, even though the graphs we're looking at aren't trees, and formally this recursive calculation only works when the graph is a tree. Okay. So BP of the message from U to V we can think of as being the BP function applied to all of the other incoming messages at that vertex. And these are just sort of marginal probabilities. Okay. One thing you can do with them, if the graph is just a tree, is calculate the partition function, so how many colorings you have. And so if you write phi-v for essentially the contribution to the partition function of the vertex V, so really phi-v should be like log of the partition function of the graph divided by log of the partition function of the graph without the vertex V. And that's something that you can work out locally just in terms of the messages coming into the vertex V. So in colorings, this would be the formula for it. And you could define the same thing for edges. What's the effect of removing an edge E? And the formula for the total number of colorings, or the log of the number of colorings, you just sum the effect, the contribution of each of the vertices, and then subtract the contribution of each of the edges. Why do you subtract the edges off? Well, each time you add in a vertex, you're sort of adding in the vertex plus all of its edges. So you're kind of, in this term, you're already getting the contribution of the edge of V, and because each edge is in adjacent to two vertices, you're sort of counting the edge twice, so you need to subtract it off. Okay, but this is a very general formula. It sort of applies to other spin systems as well. And for telling you how many, what is the partition function on the tree, and you can just prove this recursively. It's a fairly straightforward calculation. Okay, but again, just applying to trees, but part of the theory will be to sort of apply this to graphs that are not trees at the appropriate times. Okay. So, another view on this belief propagation would be that we could calculate everything iteratively. Just start off with, at time 0, we have a message at each of the vertices, and they'll just report to their neighbors what their state is. So this vertex, its message would be blue with probability 1. And then you update this by applying the BP function to all of the messages to go from t-1 to t, and you keep doing that, and essentially it's equivalent to looking at what the marginal probability would be in that subtree, looking at the boundary condition you have at depth t. And so once t is bigger than the diameter of the graph, these will be you'll get the right messages. Okay. Okay, but suppose our graph was not just a finite tree, but an infinite tree, and we want to think about infinite trees because those are the local weak limits of random graphs. So what would this procedure look like if we were doing it locally on a random graph? Well, we could do that, and suppose we started with, say, the coloring model, like the free coloring model on an infinite tree, which will just be the sort of most natural way of putting a coloring on an infinite tree. You just choose a uniform color for the root, and then for each child you take a uniform color that's not equal to its parent and just propagate the colors down from the root. So the right marginal probabilities are that every vertex should be each of the colors with equal probability 1 over q. But if you run this belief propagation algorithm, if the degree is big enough, actually most of the messages will just be stuck. They'll just be their original value, just reporting what color they have. So with a fraction that will 10 to 1 if the degree is big enough. And how big does the degree have to be for them to start being frozen? Basically q log q, which by the coupon collector problem is the point at which you'd expect a vertex to see all of the other colors in its local neighborhood. To see, like you have so the q minus 1 other color, like if a vertex is blue, there's q minus 1 other colors. If it has like q minus 1 log q minus 1 neighbors, you'd expect all of them to appear if they were independent. And if you're a bit bigger than that, it will be very likely that they all appear. And if you analyze this, essentially all of the messages become frozen. So or almost all of them. So most of the messages will just be a point mass on a single color. Okay. And so on a random graph, this procedure is no longer justified, but we could do it anyway. And the fact that the second moment method works means that a typical coloring looks like what you could call a planted coloring, which would be to just assign colors to vertices first, and then conditional on that, assign the choose the edges of the graph. And if you do it like that, you'll see that the local weak limit of the graph and the coloring on it will look like this, the colorings on these infinite trees. So if you ran belief propagation, most of the messages will just be these point masses. They'll just be reporting to their neighbors the state of their color. Okay. And so this is going to be sort of our view of how to understand a cluster of coloring. So, so how do you describe what sort of nearby colorings look like? The best way to do that is in terms of these belief propagation messages. So, so on each directed edge, we'll have a message M. So this will be just a probability distribution over the colors, and you want that they're consistent with each other. So if you take the belief propagation function of the incoming messages, you get the outgoing messages. So this is a constraint. So you could think of these belief propagation equations itself as a random constraint satisfaction problem. So so you have a set of, so the variables are the messages on the directed edges, and the constraints are the BP equations. And so the plan is to treat these collections of messages as the clusters of variables, and to sort of, so this gives a combinatorial description, and then just count how many clusters of solutions you have defined this way. And we can also give a weight to the cluster if we want to know how many solutions there are in total. So how would you put a weight on one of these clusters? Well, if you assume that if the graph were a tree, we could define the number of solutions as just e to the effect the phi of the vertex term minus, or divided by e to the phi of the edge terms, and that would give you the total number of solutions on a tree for a set of BP messages. And so we just make the assumption that that's going to work on a graph as well, and if there were enough decay of correlation, it will work. Okay, so what you have now is a new spin system. The variables live on the directed edges of the graph, and we can also give weights to the spin system according to a formula which would mean that the weight would tell you how many colorings there are in that particular cluster. So this would be a really important definition for the next couple of lectures. So this would be a good time to ask questions if it's not clear. Okay. Well, so let me tell you about how you can derive various predictions from this. So the point of view. So the ideas sort of go back to work of Parisi studying spin glass models, particularly the famous Sherrington-Kirkpatrick model. So this is a probability distribution over pluses and minuses on n vertices, and a Hamiltonian that's weighted by independent Gaussian random variables times sigma I, sigma j. And so Parisi came up with sort of many predictions about this model, and now many of them have been proved by the work of Talleyrand, Guerra, and Panchenko and others. Okay, but even as early as the mid-80s, it was sort of Mizard and Parisi and others pointed out that these are in some sense similar models to the random constraint satisfaction problems, or that they should share similar features. But they're sort of one big difference is that in the Sharrington-Kirkpatrick case, there are interactions between every pair of vertices in the graph, and because of that, you have to compensate by sort of dividing by root n for the effect of that. In the case of the constraint satisfaction problems, these are really happening on sparse graphs. There's only at least direct interactions between a constant number of other variables for each variable. And so then, maybe more recently, maybe 10 or 15 years ago, sort of based on these insights from the Sharrington-Kirkpatrick spin glass models, group of, I guess, mainly French and European physicists suggested that for a range of models, and like the ones I've talked about in like coloring, K-sat, and so on, that they should exhibit a similar collection of phase transitions, and gave a lot of detailed predictions about it. So, you can call this sort of a sort of universality class of one-step replica symmetry breaking models, which I'll just say 1 RSB from now on. So, okay. I want to say, firstly, what you should think of replica symmetry breaking meaning. In terms of replicas, you can think of that's really just another way of saying samples from the distribution. So you can think of a collection of replicas as being IID colorings of your graph, for instance. And so to divide into sort of the two cases, the simpler replica symmetric case and the 1 RSB case, there are different views you can take of what's happening. The one that's sort of maybe more natural in the spin glasses is to look at the Hamming distance when you take independently chosen solutions. So in the replica symmetric case, if you take, say, two colorings of the graph, what you'd expect is okay, actually colorings is maybe a bad example because you can just permute the labels of the colors in a sort of symmetric sort of way. But okay, so if you look at sort of the solution to the random K-sat problem, look at the number of Boolean variables on which they agree, that should be concentrated. In the 1 RSB case, that can be concentrated on two points. So if you look at the Hamming distance of the solutions, normalize them, it'll take one of two values, each with a positive probability. And roughly what that corresponds to is two cases. One is the solutions come in clusters. One case is you pick two solutions from the same cluster. The other case is you pick two solutions from different clusters. And so you get broadly speaking, two different values you can get for the distance. One can also think about the difference in terms of the clustering of the solutions. So in the replica symmetric case, you expect either no clustering of solutions, or maybe you have some clustering, but all the clusters are small, and sort of when you average over them, you don't really notice that they're clustered. On the other hand, in the 1 RSB case, we expect that a few large clusters dominate the mass of the distribution, but you don't get something more complicated. You don't get clusters of clusters or clusters of clusters of clusters, as you do in, say, the Sharrington-Kirkpatrick model. So this one-step replica symmetry breaking, you could extend to higher levels of replica symmetry breaking, where you might expect sort of more complicated clustering or the Hamming distance constant being distributed over more than 2 values. But in this class of models that we're talking about, with modulo some provisos I'll say a bit later, you only expect this one step, one RSB. Perhaps it would be more accurate to say we can only really say things when this holds. When it doesn't, then we don't really know. And the final thing is that if we look at the distribution of say colorings in the random graph, when it's replica symmetric, you expect things to be if you choose 2 random vertices, you expect the colors to be essentially independent of each other. In the case of the 1 RSB setting, they'll be correlated. Essentially, for the reason for that is that the colorings come in clusters. Within each cluster, it will look like a product measure, but then you take a mixture of product measures, and a mixture of product measures is not a product measure generally, and so you get some sort of correlation, which is essentially related to which cluster of colorings you chose. And there'll be some of the clusters that have a constant fraction of all the colorings. Okay. Since we're running a bit late, and maybe this is a good time to stop for now. And yeah, I'll tell you about the predictions in more detail tomorrow, and then how you can start to prove some of them. Okay. So.
Are there any questions? How does this this replica symmetry in one step, it translate on the computation of Zn squared?
Okay, so
Got a computation on Zn squared
Actually,
with all these.
yeah, so maybe that's better answered in the next thing I'll talk about tomorrow. So
It explains the link between these notions and second moment computation.
yeah, so okay. Essentially, well, the second moment is going to break because there'll be very big clusters of solutions that are very rare, and so rare that you don't see them, but they still dominate the computation of the second moment. And so after a certain threshold, there should still be colorings, but the typical number of colorings will be much smaller than the expected value. And tomorrow I'll talk about that in more detail.
Okay, so let's thank again both speakers this morning.